In this video, we're going to take a look at how to calculate probabilities of a Poisson distribution. Now, there's 5 examples in this video that we're going to attempt together. I'm not going to prompt you to have a go as we work through, but if you do feel confident enough to have a go, then that's great. Just obviously make sure that your solution matches what we get on the screen. Now, the reason I'm not stopping here throughout the video is because basically there is quite a lot of different ways you can be asked to find these probabilities, and I feel like for one video it's not enough to kind of present you with any questions to have a go at, but like I said, do feel free to have a go if you are confident enough. So let's start with these 2 most basic examples here. You're not really going to get asked anything like this on an exam paper. Usually you'll have context, something that looks like this. But it is important that we know how to find probabilities in the most basic case, because essentially when you've got a problem like this, you're translating it to be something like that. Okay, so what I've got here is my variable x. We know it follows a Poisson distribution with parameter 5. So if I want to find the probability that x is equal to 2, well, we just use our formula that we denoted in the last video. So this is the probability that x, our variable, is equal to little x. And that's equal to e to the minus lambda times lambda to the power of x all over x factorial. Okay, so x factorial there. Now, in this case, if we just note the values of lambda and x here, so lambda, our parameter, is 5, and x is equal to 2. So just substituting everything in appropriately here. So for the probability that x is equal to 2, then I'm going to get e to the minus lambda, so that's e to the minus 5, times lambda to the x, so 5 to the power of 2, so 5 to the power of 2, and then we divide everything by 2 factorial. So 2 factorial there. And all I need to do now is put this into my calculator and see what we get. And what I should get here, if we put everything in correctly, is 0.0842. And I've given that to 3 significant figures. Normally for exam type questions, you will be given the level of accuracy for your probability. So it might say, give the probability to 3 significant figures, or say 1 decimal place. If it doesn't give it you, then just give it to something sensible such as 3 significant figures. So that's the solution to the first example. Let's take a look at this second one here. So again, we've got our variable x. We know it follows a Poisson distribution with parameter 4. So we are asked to find the probability that x is greater than or equal to 2. And we can't just simply use this formula now. And the reason for that is because this obviously is equals. In this case, it's greater than or equal to a value. So how do we find probabilities like this? Well, we need to be clever about it. So what I do in this case is we get rid of everything less than 2 here, because we are including the 2, so we want everything less than 2. And because these probabilities will sum to 1, then we do 1 minus the probability that x is less than or equal to 1. Okay, so let's find this now. Now, to find probabilities like this, we just simply use the tables here. So this is the Poisson table. This is given in your formula book. If you're struggling to see this a little bit, if it's not too clear, then do find your formula book and make sure you can find these values. Okay. Now the way to read this table here at the top row, that's our parameter. So in this case, we're looking down 4 here, this 4 column, because our parameter is equal to 4. And the row that we go along here, so whether it's 1, 2, 0, such as, you know, all these numbers here, could be any of these, but that's given in the question. So because x is less than or equal to 1, then we're along this row here with 1, okay? And we just keep going along this row until we intersect with this column here, so we clearly get this value of 0.0916. So we do 1 minus 0.0916. Now, if I put this into my calculator, again, we don't expect you to do this by hand. What you should get, though, is 0.908. And again, I've given that to 3 significant figures. And there we have it. So that's our solution to the second example. Now, we get to the type of examples here which you are going to see basically on exam papers. So what I've been given is a bit of context here. So we've got an estate agent who sells houses at a rate of 2 per week. Best to find the probability that in a particular week she sells no houses. So how do we do this? Well, we need to translate this problem now to look something like this. Okay, so if I use the variable x here to represent the number of houses that are being sold per week, so x, in this case it would follow a Poisson distribution, and my parameter here will be 2. That's the rate. Okay, so it's a rate of 2 per week, so that parameter would be 2. Now we're looking for the probability that in a particular week she sells no houses. So what I'm looking for here is the probability that x is equal to 0. That's the probability that she sells no houses. So in that case, we just simply need to use our formula again. Remember, we use the formula here for the probability of our variable x here being equal to little x as e to the minus lambda times lambda to the x all over x factorial. Okay, so if we want the probability that x is equal to 0, then this is quite nice and straightforward. This is equal to, so let's just note the values of lambda and x here. So lambda is equal to 2, that's our parameter, and x is equal to 0. So e to the minus lambda, so that's e to the minus 2, or 1 over e squared. We times that by lambda to the x, so that's 2 to the power of 0, so that would be 1. So we'll just leave that as e to the minus 2, and then it's divided by x factorial. Now x factorial in this case, well, that's going to be 0 factorial, but 0 factorial is equal to 1. So this is e to the minus 2 over 1, giving us e to the minus 2, which is the same as 1 over e squared. So I just need to put this into my calculator, and what you should get here is 0.135. Okay, and again, this is 2 free significant figures. And there we have it. So like I said, you will be given context, but it's about translating that into a problem that looks like this. Okay, so essentially getting rid of all the context and let's just make it mathematical essentially. Now for this next example here, again, follows the same context, so an estate agent sells houses at a rate of 2 per week. So in this one, we're asked to find the probability that in a particular week she sells at least one house. So again, same context, it's a Poisson distribution with rate or parameter here of 2. Now the wording is important here, so the probability that she sells at least one house. So at least being the key word here, or keywords. So in that case, what I'm looking for is the probability that x is greater than or equal to 1. If we're looking for at least 1, then we're saying it's greater than or equal to 1. And to do this, we do it like we did for this example here. So we do 1 minus. So 1 minus the probability. Now we don't need to put less than or equal to 0. Obviously it could only be 0, so we're just going to say probability that x is equal to 0. And this one's quite nice because we've already calculated the probability of x being equal to 0. Here, we did that in the first example on this page. So we're going to do 1 minus 0.135. So 1 minus 0.135 gives me 0.865. Okay, and there we have it. So that's our probability to the second example on this page. And then we move on to the very final example here. And with this example here, we need to be careful. So let's just read the context. So what we've got is the average number of cars passing over a checkpoint on a bridge, and this is recorded as 120 per hour. Now, we're asked for the probability that fewer than 2 cars will cross in any given minute. So this is important because we start here with our interval being per hour, but the probability that we're looking for is in a given minute. Okay, so the interval that we need to go from is per hour to per minute. So how do we do that? Well, obviously in 1 hour, we have 60 minutes. So seems a bit basic, but let's just note that here. So if we've got 120 per hour, so 120 per hour, that's in 60 minutes. Obviously I need to divide this value here by 60 to get the distribution for a given minute. So if I let x here be the number of cars passing this checkpoint on a bridge per minute, so we say x is a Poisson distribution. My rate here will be 120, so it's going to be 120 divided by 60, and that will give me 2. So that's per minute. So here our parameter will be equal to 2. Okay. So like you can see, you need to essentially understand how to scale up or down our parameter. Okay. So that's per minute. Now we're asked to find the probability that fewer than 2 cars will cross in any given minute. So I'm looking for the probability that x here is fewer, so it's less than 2. Okay. Now, how do we calculate probabilities like this? Well, again, we need to make use of the table here, but we want less than 2. Okay, so how do we find less than 2? Well, that's the same as the probability of x being less than or equal to 1. We want everything less than 2. So to do that, we just look for the probability that x is less than or equal to 1. Because once we've got it in this form here, so once we've got it like this, we can just use our table. Okay, so our parameter is 2 here, so we're in this column. And our value of x is 1. Okay, so we just go across 1 here, and so we get to this value. And like we can see, we get 0.4060. So we get 0.406 to 3 significant figures. And there we have it. So, like I said, that's 5 examples that we've covered in this video. Hopefully it makes a little bit more sense. We're going to do a lot of probabilities throughout this chapter. So make sure you keep practicing these. Like I said, we'll see more even in the next video. But hopefully this has helped. So in the next video, we're going to take a look at adding Poisson distributions.